The subject of today's video will be different properties of triangles, and we can describe triangles by two different classifications. First, by classifying how they are in terms of their interior angles, and secondly, in terms of their side length. Let's begin with angle classification. If all the angles inside the triangle are acute angles, that is, angles less than 90 degrees, then we call the triangle an acute triangle. If one of the angles within the triangle is a right angle, that is an angle measuring 90 degrees, then we call the triangle a right triangle. The final classification based on angle measures is if one of the angles within the triangle is an obtuse angle, that is greater than 90 degrees but less than 180, then we call the triangle an obtuse triangle. So these are the different ways we can classify triangles based on their interior angles. Now we can also classify triangles by their side lengths. If all the side lengths of a triangle are equal, that is known as an equilateral triangle. And we indicate that all the side lengths are equal by single lines through each of the equal side lengths. So this line means this side length equals this side length, which is equal to this side length. Now it happens to be if all the side lengths are equal, then we also know all the angles are equal. Each of the interior angles would be equal to 60 degrees in an equilateral triangle. Now, if only two sides of the triangle are equal, this is known as an isosceles triangle, and we indicate the two sides are equal again by the lines through the equal side lengths. Our final category is when none of the side lengths are equal, and that is known as a scalene triangle. An important rule to know about triangles is no matter what type of triangle it is, if you add up the three interior angles of the triangle, you will get 180 degrees. So every triangle is made up of three interior angles. The sum of these three interior angles is always 180. With that in mind, let's solve the next example. So here we have three interior angles. The first one is measured to be 2x plus 1. Our second angle is 5x plus 5. And our third angle, indicated by the square in the corner, is indicating this is a right angle or 90 degrees. So we have the three interior angles, and we know by the rule above that if I add together the interior angles, we should get 180. So this tells us 2x plus 1 plus 5x plus 5 plus 90 degrees is equal to 180. So I took the three interior angles. If I add their angle measures together, we know we get 180. And now we can begin to combine like terms. We see 2x's plus 5x's would give us 7x's. 1 plus 5 plus 90 will give us 96, and that's equal to 180. So we use this knowledge about how the interior angles of the triangle add up to be 180. We were able to create an equation, and now we can solve the equation and get x by itself, and we'll be finished with the problem. So we begin by subtracting 96 from both sides. And when we do so, we're left with 7x on the left side will be equal to 84 on the right side. Next, we can divide both sides by 7. And we see x is equal to 12. So as we continue with other examples, do keep this idea in mind. If you add all the angles of the interior of a triangle, you will always get 180 degrees. Now as we go through our next key idea, let's look at the triangle in the example below to help us make sense of the different terminologies. So we first have the idea of the measure of an exterior angle. So in this example, that would be this angle measure of 124 because it is exterior outside of the triangle. Furthermore, if you continue out the triangle's line, which is what we had here, the line that makes with the flat ground up to the outside edge of the triangle, that's what's 124, and that's our exterior angle. Now it says this measurement is equal to the sum of the measures of the two opposite interior angles. So by opposite interior angles, we mean to focus on the exterior angle, and then the angles opposite from that, the two of the three that are opposite, those are our opposite interior angles, not the one that's right next to it, but the ones across the triangle from the exterior angle. So based on this rule, we know that 124, the exterior angle, is equal to the sum of the two opposite angles. So we know this one's 77. We know the unknown one is written by question mark. So we can solve to get the unknown measurement by subtracting 77 from both sides. And when we do, we get 47 is equal to the unknown angle. So this we reasoned based on our exterior angle measure. I only knew one of the measurements inside the triangle. So to find the missing measurement, we had to look at our given exterior angle and know that its value is equal to the sum of the two opposite values. Our next topic is similar triangles. So whenever we mention the phrase similar triangles, we mean two triangles that are exactly the same shape, but not necessarily the same size. So the idea is they might be different sized triangles, but their proportions are exactly the same. So for instance, one triangle might be double the other triangle. And because they have this proportionality or this same property between the two triangles, even if they're different size, we know a few things about similar triangles. First, we know that corresponding angles must have the same measurement. So what do we mean by that? For instance, here I've got two similar triangles. We are told that this triangle is similar to this triangle. We see they're oriented in the same way. It looks like this is the longest side length in both of them. So by saying corresponding angles have the same measure, the angle opposite the longest side length in the smaller triangle would have to be equal to the angle opposite the largest side length in the bigger triangle. Similarly, the angle at the peak of the lower triangle is equal in value to the angle at the top of the peak of the larger similar triangle. Similarly, this angle, which we're highlighting here in pink, would be equal to this angle in the similar triangle. So we know that corresponding angles must have the same measure in a similar triangle. The other known aspect of similar triangles is that ratios of the corresponding side lengths must be constant. So if one side length is exactly twice the side length in the original triangle, all other side lengths must be multiples of 2 as well. Suppose we're told that we have two isosceles similar triangles, drawn here in the middle of the screen. If we're told that these triangles have the following measurements along their side length, so this side length is 4, as this is an isosceles triangle, we also know this side length is 4. We know that the shorter side length in our isosceles triangle here is 2, and then we can compare that to the corresponding location in the larger triangle. What was side length 2 in the smaller triangle is now side length 8 in the bigger triangle. What did we have to multiply 2 by to get 8? We multiplied 2 by 4 in order to get 8. So what that means is our smaller triangle, if we multiply it by 4, we get the size of the bigger triangle. So that must be maintained for all the side lengths. So we know this is side length 4. So in the larger triangle, it must be that side length times our constant multiple of 4, and we get the side length 16. Now, as this is an isosceles triangle, we also know this would have to be side length 16. So that's the idea of what we mean when we say the corresponding sides. If you multiplied by one factor to go from one side length to the larger side length in the bigger triangle, you have to multiply by that same factor for all of the different side lengths in the smaller triangle. Let's see some more questions about similar triangles, and we'll try to go through these ideas further. In our next example, we have a child is 1.2 meters, and the child is standing 11 meters away from a tall building. A spotlight on the ground is located 20 meters away from the building, and it shines towards the wall. How tall is a child's shadow on the building? Let's take a moment to make sense of this diagram. So here we are told the child is 1.2 meters, and we see this vertical height is 1.2 meters, so it makes sense that this is the child represented in the drawing. And we're told the child standing 11 meters away from the tall building. Well, we see 11 meters here as this horizontal distance from B to C. That's our 11 meters. So at point C, we've got our building. We're told a spotlight 20 meters away from the building is shining towards the wall. So here's our spotlight. It's shining in this direction. And as the spotlight is shining behind the child's shadow will be cast towards the building approximately to this height h. So whenever we're asked to solve the problem, we're interested in the height cast by the child's shadow, which is represented by h. Now in this problem, can you see that we have one bigger triangle, and within the bigger triangle we have a smaller triangle inscribed within? Whenever you see one triangle inscribed inside of a bigger triangle, that's an automatic giveaway that we have similar triangles. So the proportions of the smaller triangle are related by a constant multiple to the proportions of the larger triangle. So all we need to do is figure out how are the different aspects related, what do we know of one, what are we looking to find in the other. Now, one thing that we have a lot of information about is horizontal lengths. We know this overall length that I'm highlighting here is 20, and we know the shorter length from here to here is 11. Based on that information, what could you determine about the length from A to B? The length A to B is going to be the overall distance of 20 minus the part that we don't want, 11. So we see this is 9. Now, whenever we talk about similar triangles, we have to relate similar aspects. So for instance, I see in our triangles, here we have our 90 degree, and here we have our 90 degree. So the straight side length that's flat against the 90 degree are 9. That's related to the larger triangle side length of 20. So here we're looking for related things. We want to then relate the thing that we're looking for, the height of the child's shadow in the building. Well, the height here from the right angle up to the angled portion of the triangle is equivalent in the smaller triangle to the height of 1.2 meters. And this is where in our last definitions it said the ratio of the side lengths must be constant. If I compare that in the shorter side length, I've got a 9 over a 1.2, so where are these numbers coming from? We see the 9 is the longer straight side length. The 1.2 is the shorter straight side length, or the vertical side length. Both of these are relative to our smaller triangle. Since it's proportional to the larger triangle, this would have to be equal to the corresponding side lengths in the bigger triangle. So 9 is this horizontal side length. So what's the corresponding horizontal measurement in the bigger triangle? That would be 20. So like things have to go in like locations, horizontal side length here, horizontal side length here. Similarly, 1.2 is a vertical side length. So the vertical side length of the larger triangle has to correspond on the other side. And now we have a proportion involving our missing piece of information. So this is a particular approach that you can do whenever it's similar triangles. You can set up a proportion like things in the smaller triangle relate to like things in the larger triangle. And now to get h by itself, we notice h is on the bottom of division. So remember, whenever you're solving with algebra, you do the opposite. So h is currently dividing 20. So to get rid of it and maybe isolate it, I'm going to multiply both sides by h. What's done to one side should be done to the other. And this will cancel the h on the left, which will make this look simpler. We'll just have a 20 left. But on the right, I've got h times 9.2. Excuse me, I misspoke there. H times 9 over 1.2. Now 9 divided by 1.2 is 7.5. So this will become 7.5h. So keep in mind the 9 divided by 1.2 is how we got the 7.5. And now I can get h by itself. H is currently being multiplied by 7.5, so divide both sides by that. And we get h would be equal to 2.66666. So let's round this to 2 decimal places. So we know we keep the 2.6. We look at the second decimal place. One after it is a 6, which is 5 or greater, so this rounds up to 7. And all the units of distance in this problem were meters, so our units would be 2.67 meters. So our next problem is also a similar triangle. It says a forestry official whose eye level is 2 meters above the ground wishes to find the height of a tree. Now you can measure the height of the tree in this very interesting setup. It says he places a mirror horizontally on the ground 20 meters from the tree and finds that if he stands at the point C marked below, that's 4 meters from the mirror, he can see the reflection to the top of the tree. So he's figured out the exact location. The mirror is horizontal on the ground floor of the forest. And if he walks back a certain distance, he can now see the top of the tree. So what that's doing is it's creating a straight line from the mirror to the top of the tree, which forms a triangle. And then that also follows back to his line of sight, which forms a correspondingly smaller triangle. We're asked how high is the tree. Now in order to figure this out, we're given enough information about the triangles to realize they're similar triangles, even though it did not say they're similar triangles in their problem. The information that we need to focus on is, first of all, these are perpendicular heights. So the ground to the tree, the person to the ground, both of those share 90 degrees. Additionally, we can see here that we've got a single arc mentioned in this angle, a single arc mentioned in this angle, and what that means notation-wise is these angles are equal. That's the notation. If we ever want to indicate angles are equal, we use the same line across. Now, we have this angle plus this angle plus the unknown angle has to equal 180, but if we notice, these are the exact same. So each triangle has the same 2 of the 3 angles. So whatever the missing angle is, both of these triangles have to share that missing angle. So the angles are exactly the same, which means the triangles are similar. Anytime you know that 2 triangles have the exact same angle measures, that's how you know they're similar. So since the angles in both triangles are the same, we know they're similar triangles. And with that, we can use a lot of information about the smaller triangle, which we could measure, the individual's height, the distance he was from the meter, and then extrapolate that out to the larger triangle. We know the distance horizontally of the smaller triangle is 4 meters. Can you find the corresponding horizontal distance in the larger triangle? Identify that in the image. The corresponding longer horizontal distance is 20. So if these are similar, we know they're multipliers of each other. 4 times what gives you 20? What do we have to multiply 4 by to end up with 20? Well, that's 4 times 5 is 20. So this means to get to the smaller triangle to the larger triangle, we multiplied each side length by 5. So with that in mind, if you know the smaller triangle has a vertical height of 2 meters. What does that mean our taller triangle would have a height of? It would be 2 times 5, which is 10 meters. So the tree is 10 meters tall. Now that's one way you can think about the problem. You could also set up a proportion like we did in the last example. To illustrate that, remember you do same triangle equals the same proportions in the other triangle. So I could do the vertical height divided by the horizontal height. And in the smaller triangle, the vertical height is 2, corresponding to a horizontal height of 4. And then we know the vertical height. At this point, we hadn't solved for it yet. We could call that x, divided by the corresponding horizontal length of 20. And now we can get x by itself. I'll multiply both sides by 20. Cancels the 20 on the other side, so we get x is now 2/4 is 1/2, so that's 20 times 1/2, which is 10 meters. The same answer we got before, this is just solving it in a different way. So keep in mind, how do you spot similar triangles? Sometimes, as in our previous example, you see a smaller triangle inscribed within a larger triangle. That's a dead giveaway that the two triangles are similar. In other examples, the triangles aren't inscribed, but we're given enough information about the triangles to realize they have the exact same angle measures. And whenever they have the exact same angle measures, we know they must be similar triangles. Now, the last topic of this section is the Pythagorean Theorem. The Pythagorean Theorem only applies to right triangles, that is, triangles where one of the angles is 90 degrees. Now, in a 90-degree or right triangle, we have 3 different side lengths, A, B, and C. A little bit of terminology. Do you see the side length that's directly across from the hypotenuse, that's side length C? The hypotenuse, or the length across from the 90-degree angle, will always be the longest side length. So we have the Pythagorean Theorem, which relates the different side lengths together. It tells us that one of the shorter side lengths squared, A squared, plus the other shorter side length squared, is equal to the hypotenuse squared. So we have A squared plus B squared equals C squared, where it's implied C is the hypotenuse of the right triangle, A and B are the shorter side lengths. Let's see how we can apply this to a problem below. So in this example, we see a right triangle drawn. We know it's a right triangle based on this right angle inscribed within here. This is our 90 degree. We are told the side length of the hypotenuse, the angle across from the right angle, is 12. And then the shorter side lengths have length y and length 8. Now, we need to use the Pythagorean theorem to find y. The Pythagorean theorem relates side lengths of a right triangle. So we know the formula goes the shorter side length squared, so 8 squared plus y squared separately, equals the hypotenuse squared. And that will be 12 squared in this case. Now in our calculators, 8 squared is 64. Y squared we don't know, so I'm just going to leave it as y squared. 12 squared in your calculator is 144. And now we can solve to get y by itself. Let's subtract 64 from both sides. And we would get y squared equals 80. Now in order to get y by itself, we'll need to take the square root. Now we take the square root of both sides. That's raising things to the 1/2 power. So let's look for this in your calculators. On my calculator, do we see it described here? Looks like the square root of x. So what I would do is I would do 80, then the square root, and we get the value 8.944. So if you're ever trying to get y squared by itself, square root both sides. And let's round this to about 2 decimal places, 8.9. We look one past the 4 is a 4, that's less than 5, so it stays the same. About 8.94 would be our missing side length. So let's just recap a few of the rules that we learned. We know that there are 3 angles that are interior to any triangle. If you add all those angles together, it will be 180 degrees. We know the exterior angle of a triangle is equal to the sum of the opposite angles. We learned that for similar triangles, those are triangles that have the exact same angle measure. Although they're not the same size, they are proportional. You can use information of the smaller triangle or the larger one to find out information about the other one based on the ratio of their side lengths. And then finally, if we're dealing with a right triangle, we know there's a special formula that relates the side lengths of the right triangle. That is the Pythagorean Theorem, and it states that the 2 shorter side lengths squared, a squared plus b squared, would have to equal the longer side length, or the hypotenuse squared, which is our c squared. So as always, if you have questions about the material, don't hesitate to reach out, and I'll be very happy to help you.